yeah, it's not going to be a main focus of the class, but I do want to introduce it because it'll show up later if you do more work on PDs. Okay. All right. So we have about 8 minutes left. So that's basically what I wanted to say about Fourier transforms. If I could just start by briefly introducing the next topic of the heat equation, which is the maximum principle. Okay. So so we've talked some about energy arguments for uniqueness. The main idea with the maximum principle is that smooth solutions to the heat equation, okay, which we should typically expect because the diffusion operator is smoothing, they're going to attain a max and a min, okay, either initially or on the domain boundary, okay? And so what does this mean? Well, it means that, if I start off, you can think of it intuitively, right? If I start off with some, peaked function like this at time equals 0, right? What I should expect at time greater than 0 is that this is going to be smoothed out. And in particular, we're mostly going to deal with bounded domains, so that either heat is sort of getting sucked out the domain wall here, x equals a and x equals b, or there's a no flux condition, so the heat is stuck here inside, right? And it sort of should make sense, right? Because what's happening is smoothing. Any irregularity in my initial condition, or any basically large deviations in the shape of my initial condition are immediately going to get smoothed out as I move away from time equals 0. Okay, so the extremes of my functions are going to get smoothed out in favor of more and more constant-like looking functions. And so that's kind of the intuition behind the maximum principle. We'll get more into the nitty-gritty on Wednesday on how it all works. Okay. But what I want to ask about this is, do you think that this holds, okay, for the wave equation? Do you think that we could prove a maximum principle for the wave equation? Yeah. So can you think, so that you can't. Can you think of how you would construct a counterexample in the case of the wave equation to show that a maximum principle doesn't hold?
You could have like two bumps or something just traveling towards each other, and they superimpose, they would reach a maximum.
Right. So let's say we have some bounded domain here, right? These are going to they're gonna propagate right and left, right, and they're going to be integrated as well. Okay, and so at some later time, you could have some, maybe you'll have some bump over here, right? But then in between, you're going to have some hump here whose height is higher than the original height of your bumps, right? Or you could have 3 bumps or something like that, and they could sum up, or you could have 4 bumps or something like that. And because the bumps are just going to propagate, and if there's any initial velocity as well, that's going to be integrated as well. You can have solutions on the interior, okay, that have a higher peak than the initial condition, or any values of your function on the boundary, right? So that's a hand wave example, but you can also sort of construct those more carefully by hand in a problem. Okay. So that's the contrast, right? So remember, heat equation is it's like a canonical form of a parabolic versus a hyperbolic equation, and the maximum, so the maximum principle holds in the case of heat equation, but it's not going to hold in the case of a wave equation. So so some notation, right, in order to motivate this idea, and then I'll stop for today. Okay, the way that we're going to set this up is that not only are we going to bound space, but we're going to start by bounding time. Okay. So what I want to do in order to prove this, right, is I say I'm going to have some region in X that goes from 0 to L, and I'm going to have some region in time that goes from 0 up to T, and I'm going to make this a box, right, that I'll call UT, and the end of this box I'm going to call UT. Okay, but then the boundary here, the boundary here, and the boundary here, I'm all going to call the boundary of my region. Okay, and what I want to do is I want to essentially prove the maximum principle for this box, and then I'm going to take the limit as t goes to infinity. So basically, for a box of any size, for a box of any ending time, the maximum principle is going to be satisfied, and so then I can basically capture all time. The limit as t goes to infinity. Okay, so u, right, I'm drawing it in just one-dimensional space and time, but u could be in Rn here. Okay, this is our domain or set, right? So X could also be multi-dimensional. U sub t is going to be a parabolic cylinder. So it's going to be U, okay, or initial, our domain here excluding initial time, and including the end time here. So this should be an open boundary of the interval here. Okay. And gamma here, gamma t, is going to be the closure of U, okay, with U sub t removed. So it's going to be the boundary of U along with the interval from 0 to t, and then also united with U crossed with t equals 0. Okay, so this is going to be our parabolic boundary. Okay, and then I'm going to have a C2 function in X, and it's going to be C1 in T. Okay, and so little u is going to be my solution, right? And u sub t, the gradients in X of u, and the gradients in X of u, these could be potentially mixed partials. These are all continuous on u sub t, right? And u here is going to be my my initial interval from 0 to L, which is in X, right? Okay. And the theorem basically says that the maximum of I am running out of time. The theorem here basically says that the max over u sub t, its closure is equal to the max over that boundary of u of xt, okay? And the way that we're going to prove it, okay, is just to use a sequence of inequalities that we can get by applying the diffusion operator, which I'll do next time. So that's the setup of where we're going with the maximum principle. I'll get into more detail next time. But I think that's enough for today. Okay. All right. So that's all I have for now. And let me know if you have any questions. I can start office hours now as well if you have questions about the homework. Otherwise, see you all on Wednesday.
Thanks, Zach.
Thanks.
You said that you aren't going to be available for usual office hours tomorrow, but we can schedule something if needed.
Yes, exactly.
Okay. Great. Thanks.
You're welcome.
Professor?
Yes.
So in chapter 5, question 6, like we were given u of x, the initial condition as h of x is e power minus x, and we had our equation ut equal to kuxx, I think the heat equation. And yeah, so the solution is given by integral of minus infinity to infinity phi of my x minus y comma t, which is the fundamental solution, that convolved with the initial condition g of y, right?
That sounds right.
So basically then we get a really messy integral, right? A very complicated, very messy integral in which we have like 1 over square root of 4 pi kt with the integration of the delta function h of y